Green Rush, Mining the Energy Revolution with Matt Watson.
Hello and welcome to Green Rush, Mining the Energy Revolution. I'm your host, Matt Watson. Each week we dive into the periodic table and take on another couple of elements. This week we're going to talk about a revolutionary new copper, platinum group metal, and e-waste processing technology brought to us by PH7. Our special guest is Mr. Mohammad Doostmohammadi. He's the CEO and founder of PH7 Technologies. Mohammad, welcome to the program.
Hey, thank you so much for having me here. So excited to be here and have this conversation with you.
Fantastic. Well, let's get into it. I grabbed a screenshot of your homepage. Why don't you tell us a bit about PH7, how long you've been around and what you're all about?
Yeah, so PH7 Technologies is a clean tech company focused on extraction of critical metals vital for energy transition and electrification. And we do this through our proprietary closed loop process, combining organic, inorganic, and electrochemistry together. And we extract these metals in a manner that doesn't generate any wastewater, any effluent, any off-gassing, while we reuse the chemistry over and over and over. We started with 2020, founded the company. We built our state-of-the-art R&D lab in 2021, early 2021, and built our first pilot plant in early 2023. So we started with PGM platinum group metals, extraction of that from spent catalyst and recycling materials, and we added more metals to our portfolio. We added copper, and now we are adding gold, silver as well to be able to extract these metals from electronic waste and end-of-life printed circuit boards, and continuing the R&D to add more metal portfolio to our closed-loop extraction process.
Great. So let's dive into these four different buckets that you were talking about here. Let's start off with the PGMs. And like you said, it sounds like your feedstock is largely catalytic converter, end-of-life catalytic converters and the waste streams that come from that. One of the first things that pops to mind when I looked at your website is just the complete bucket here. Most AutoCat recycling systems, as you know, aren't necessarily geared to recover iridium or copper or tin, and certainly gold and silver is unique. But your system, obviously, as you just described, is capable of doing them all, right?
Yeah, so we extract these metals depending on the source of the materials that coming to us. So for example, for catalytic converter and a spent catalyst, it's mostly platinum, palladium. If they have rhodium, we can extract rhodium as well. And if there is iridium, which is, for example, hydrogen electrolyzer membranes or electrodes with iridium oxide, or even spark plugs, that's another R&D that we did, and we are actually building an operation plant, going to be operational hopefully in September, October this year, that we can extract iridium and platinum from spark plugs as well. Copper, gold, silver, tin is mostly from the electronic waste materials that we extract from end-of-life PCBs. And if we have some copper in a spent catalyst, we can extract the copper from that as well. But not much. It's no grade of copper in the materials that we receive.
So just to kind of help frame the market in terms of auto catalyst, I had a slide. This is a slide that depicts how much platinum, palladium, and rhodium goes into light duty and heavy duty combined, all catalytic converters globally. And you can see there's been a huge ramp in the amount of PGMs that go into the system, peaking at close to 13 million troy ounces a year. And we're in a bit of a decline, mostly because auto sales have declined so much overall. But with this and the vehicle lives approaching 20 plus years in life before they get to the scrap, it's what I depict as being the largest platinum group metal pool account in the world. And to give people a reference, in 2004, with some 600 million vehicles on the road, 35 million troy ounces of platinum, 43 of palladium, and 8 million of rhodium. By this year, 2024, you can see those numbers have grown. Of course, there's some 1.4 billion ICE vehicles on the road, and then projecting forward 20 years from now, that'll grow even further. So this is a sizable population of metal that's out there, and just to give people a sense of the value proposition of being in the auto catalyst recovery business, there's a whole lot of metal out there yet to be recovered. So I don't know if you have any comments there, Mohammad.
No, absolutely. I believe this AutoCAD market is actually growing. The demand is growing as well, and while we have this many cars, as you mentioned, 1.5 billion of the car on the road by 2040, these going to get to their end of life. And these precious metals, this really critical metals such as platinum, palladium, rhodium, needs to be recycled, extracted, and being implemented in new technologies. So as you know, hydrogen is relying on platinum and iridium. So one of the major source of platinum will be this AutoCAD. Will be new applications for palladium and rhodium. Definitely that's going to be, there are lots of application under R&D, but by 2050, we will see the role of application for these two metals as well.
Right. Now, palladium, I'm a bit concerned about, just the sheer abundance of how much we're going to recover. The palladium market could push into surplus. So there's lots of concerns on the outlook for the pricing of palladium and developing new demand sources to take up that slack, if you will. But you're exactly right. I think that the platinum and the blue in particular is going to be highly valuable going down the road with the hydrogen economy. And even rhodium, which is very much catalytic converter dependent today, there's a whole bunch of uses for it. I'm more optimistic on the rhodium having a home, but certainly the palladium is a concern. There'll be future programs that I'm going to dive in deeper into next generation applications for that palladium. So, but when you look at the conventional autocatalyst and PGM processors today, it's completely a hydrometallurgy based process, and your approach is different. I grabbed this from one of your presentations, just kind of highlighting some of the differences. I don't know if you want to go through some of the highlights of this, Mohammad.
Yes, that would be great, actually. So our process is completely different from pyrometallurgical processes. So pyrometallurgy has been, I believe, operating for the last 1,000 years, and we're always melting, burning things to extract the things, valuable things out of that. And that practice has been evolved. We will see lots of revolution in furnaces and other practices, but the idea, the concept is the same. You have to melt down the whole matrix, everything together, to be able to extract the metals. And as you know, the metals are only 0.1 to 0.5% of the whole volume that you melt down. Our process actually has a completely different approach. Instead of attacking the whole matrix and extract the metals, we attack that 0.1 to 0.5% of the PGM, the valuable metals, and we extract them, dissolve them into the solution. And doing so we're not going to be relying on a matrix. Whatever matrix can be formed into the powder can be pumped through our reactors. We can extract it. So we don't have the limitations that we see in pyrometallurgical methods. So for example, if the melting temperature is really high, like silicon carbide or titanium, zirconia titania, which is really hard for melting it down in furnaces, we can easily process those type of materials. So I see PH7's process as complementary to pyrometallurgical processes. There are some materials that we cannot process, the materials that cannot be formed into the powder. It's impossible for us to process it because we cannot pump it, we cannot run it as a slurry through our leaching reactions. But the materials that is problematic for smelting furnaces can be easily processed through our processing plants. We don't have any penalty for any of high carbon content. We are not really concerned about any carbon content in the materials. No concern in zirconia and titanium, iron content, or any other elements that is there is not a concern for us, which as of today, it's a concern for pyrometallurgical methods. Our whole process is actually faster. It's getting, we get to about plus 50% purity of the PGM after receiving of the materials in less than a week. So it goes through the leaching process very fast and coming out of our electrowinning process at the end of the process in less than a week. And then it goes to our refining partners that will be refined to separate it to 99.9% platinum, palladium, and rhodium. So it's a very fast process and fast turnaround of the materials. Still, we have the bottleneck of the refining because refining should happen, but we are working with our partners to accelerate that one as well. Overall, it's way less energy consumption in our process comparing to smelting practices. The main reason is the temperature. So we extract these metals in way lower temperature comparing to smelting furnaces. If, let's say, it's 1,000 to 1,500 degrees centigrade of furnaces, they need to melt down the matrix. Our extraction is happening somewhere between 70 to 90 degrees centigrade. That's the all temperature that we need to dissolve the PGM into the solution.
And I want to stop there and emphasize this because, I don't know how much Americans have a sense of this, but in Europe, there's really been a challenging of the heavy duty industries, whether it be, high energy intensive, ammonia processes or smelting, steel, aluminum smelting. All these processes are a bit under attack in Europe due to the high energy prices now that Europe is faced with. I think one of the biggest sales points for your technology is the power consumption, and the temperatures are so much lower than the conventional pyro process. So I think that's a big sales point for your technology myself. Your thoughts?
Oh, absolutely, you're right. And especially in Europe and Asia, where you see that actually the electricity is more expensive comparing to North America. It shows itself. It highlights the value of our technology. And definitely that's one of our actually visions at PH7 to design the processes that consume way less energy, way less water and resources to extract these metals.
Good. So, and it kind of stunned me as I've, been listening to your material for the past couple of years in different presentations. This ability now to impact the copper world, and really, you're looking at copper recycle as another stream, but primarily you started off with looking at primary ore bodies and how you could impact the processing of copper ore. How did you get into this market? How did you lead to this point?
Yeah. So that's actually a very good question. As I mentioned, we started with PGM, recycling of the PGM and extracting from those resources. And while we were doing that, we saw that actually we have the ability to extract the copper. And I started doing some test work on the copper, different copper sources of the materials. And one of them has been copper sulfide ore. So as you know, copper demand is increasing. If you like it or not, electrification requires copper. And copper is, I believe, the main critical element and metal in just the whole critical metal portfolio. And 80% of our resources of the copper mining is coming from sulfide ore. So only less than 20% is oxide ore, which is easy copper, which can be leached, can be extracted through the chemical reactions and leaching reactions. Unfortunately, 80% is sulfide, which is impossible to extract with existing chemistries, existing leaching opportunities in the market. So everything is happening through the extraction of the copper from the copper sulfide through the flotation concentration and then shipping overseas to smelters and melting down the sulfide copper concentrate to extract the copper. So what we are offering actually, and what we have been focusing for the last 2 years of R&D was enabling the heap leaching process, what is happening in oxide ore into the sulfide ore. So heap leaching process, which is a very low cost, environmentally friendly process, doesn't need really fine grinding. You just have a jar crusher, and after the first crusher, it can go to a heap leach and you circulate your chemistry through it. And then there is no wastewater, there is no tailing ponds. It can be the reclamation of the site is very easy comparing to the sulfide ore. So what we are targeting to do at PH7 is enabling that heap leaching process for sulfide ore and enable it for all the entire mining operations. And how we do it is actually, again, through our electrochemical process and organic ligands that we developed that can extract the copper, can oxidize the copper, and leach it into the solution. So we can break down the sulfide copper bond and oxidize the copper through those electrochemical reactions and then bond it with our organic ligands to dissolve it into the solution.
So I tried to take your video and break it into just a couple panels here, 2 slides of 8 panels. So you take your crushed ore, you spread it out in some sort of field or system, and here this is where you start your dissolution process right away. You get it into a pregnant solution is what you call it. Can you explain that a little bit more?
Right. Yeah. So when we crush it, it goes to the heap that has some slope. From the top, you start irrigating it with our chemistry. So our chemistry will pass through the crushed ore, and while it's passing through this crushed ore, which is permeable because it's not fine, it's about 1/2 inch to 1 inch size of the ores, the rocks that we have in that pad, then it starts dissolving the copper into the solution. And after it dissolves the copper into the solution, it will be collected in the downstream, in the downside of the pad. And when you're collecting it, it goes for extraction. It goes for the regular typical solvent extraction electrowinning systems that is being applied in oxide, or we can use the existing facilities if they already have it in the mine. So it's adaptable with the existing flow sheets. And after solvent extraction and electrowinning, which means that we transfer the copper from our solution to a specific solvent, and then from that solvent to a sulfuric acid solution, and that sulfuric acid is being circulating through an electrowinning system, and then you have your copper cathode at the end of the process.
I was, if you don't mind, I wanted to ask this electrowinning. Now, are there mixed metal oxides on this electrowinning process?
No, for the copper process, no, we don't use any mixed metal. But for our PGM process, yes, we do have actually mixed metal process. For electrolyzer, so if I continue in here after our solution is being just stripped, so the copper transferred to the electrowinning process, now it's a barren solution, doesn't have any copper in it, it goes to our electrolyzer. So we actually invented and built an in-house electrolyzer that being used to regenerate our chemistry. It's the same electrolyzer that we are using in our PGM process, and it's the same in a copper process. The copper process is way larger. It's just the scale is way huge because we are talking about thousands of tons of the materials that we are processing per day. And that electrolyzer regenerates the solution, reactivate the solution, and then it goes back to the pad again, irrigate again the rock, the ores, and dissolve the copper. That electrolyzer that you see in picture number 5 is where we are actually using metal oxide in our anode, coated with metal oxide in the anode.
Fantastic. Okay.
And as a byproduct of that electrolyzer, we produce hydrogen. So it's a kind of acidic electrolyzer. So it's not chloralkali. It's kind of organoacidic electrolyzer. That's what we call it. And as a byproduct of that electrolyzer, we produce hydrogen. Per ton of copper that we are producing on site, on a mining site, we produce about 40 kilo of hydrogen that can be captured, can be purified, can be compressed, and can be used as energy storage, can be used as a fuel for haul trucks, or any other application. If there's natural gas, can be blended into the natural gas and feed into the system.
Really, that's fascinating. So where are you at in terms of setting up and doing a scaled demonstration of this? What's the timeline look like?
We are actually building our pilot plant, off-site pilot plant in our facility in Metro Vancouver. Being operational, we have a prototype operational right now, and our pilot is going to be operational by the end of this year, with the hope to have an on-site pilot in one of our mining partners' sites toward the end of next year. And the following year will be the commercialization of our process, again, in one of our sites of our mining partners. So right now we are receiving the samples from different mines around the world. We are open to receive more samples. So any mining companies that they want to test their samples with our technology, we offer a free testing. We test their samples and share the results and the full report at the end of the test works. And from that test work, we can design an on-site operation for them that can extract the copper, and literally we can increase the supply of the copper from a sulfide ore mine by 2 times. So as you know, in a sulfide ore mining, when they do the concentration, they have a cutoff grade. And what does cutoff grade means? That if it's lower than the certain amount of the grade, it's not economical to extract it, so it's going to be waste, and it's called waste rock. And that grade is nowadays about 0.2, 0.25%. So anything less than 0.2% going to waste rock. So it doesn't go to a crusher, grinding, or anything. It's already mined, but they're not going to be processed. So what we are offering, not only existing ores that they are processing, we can extract copper from their waste rock. So we can go all the way down to 0.05% copper and still economically extract the copper through our innovative heap leaching process for sulfide ore.
Right. There's previous episodes where I've talked about the ore grade declining over time on copper, and I think the global average ore grade today is like 0.73%. But of course, there's going to be portions within that deposit that are going to be much lower. So I got to believe there's a lot of copper mining folks who are very interested in this technology and shaking this thing out and seeing what you could do in scale. Because if you could recover at that low of rate, that really solves a lot of issues that are just going to compound over time as we get into lower and lower grade ore grade bodies, right? There's no avoiding that. it's coming our way, whether we like it or not. So, can you talk a little bit now on copper recycle? You're not necessarily in the copper recycle today, but there's you say you're exploring this space. Can you talk a little bit about what you're doing here?
Yes. So one of other approach that we have is extracting the copper from end of life materials, which is with a focus on electronic waste, end of life printed circuit boards, and that's our main focus right now. And we've done a lot of testing so far. We are developing a prototype, actually going to be operational in the next couple of weeks, and with the goal to build a pilot operation for our e-waste process early next year and commercializing it even next year. So we are working with a couple of e-waste partners, recyclers, and OEMs that we can extract these valuable metals, including copper, from end-of-life printed circuit boards. And we're not only extracting copper, we're extracting gold, silver, palladium. And on top of that, which smelters cannot recycle, is tin. We can extract tin with our process from those end-of-life printed circuit boards and having it back into the circular economy.
I was going to ask, because a lot of the copper waste streams, as you probably know, I think it's some 75% of the copper is in the form of wiring. As you know, there's a lot of chipping equipment that you can buy that breaks the insulation away and segregates with pretty high degree of segregation, pure copper in one bucket and all the plastics and insulation in another. It seems like a lot of the waste streams are fairly high purity to start with in the recycle world. And I wasn't sure how well your process would tend to that, but I think you're answering the question. In the form of e-waste, of course, it's a much lower grade and diluted source, if you will, of copper. So there I see a better fit, if you will, for your technology. So let's get into that. That's a good segue. So e-waste, a big and growing market, as you know. I could recite the stats, but I think this would fit quite well in this marketplace as well. So why don't you talk us through what you're doing here? And I do have the graphics of your process if you want to walk through it as well.
Yeah, no, absolutely. So in e-waste world, you know that e-waste can be a computer, your laptop, your TVs, low grade, high grade, mid grade. There's different type of e-waste that contains those printed circuit boards. Our goal is actually to get to the printed circuit boards because we are not a plastic recycler or aluminum recyclers. We are focusing on critical metal extraction from these materials. So just if you see in first slide is actually where the material preparation is being done. It's mostly being done. It's a really good established industry on the recycling side. So all of these computers, laptops, iPhones, whatever, it goes to a shredder, shredding it down, and then you remove it, separate different type of big chunk of metals after shredding it down these e-waste. So including steel will be removed by magnet removal, and then you remove aluminum, mostly with an eddy current, and then optical sorter will remove the plastic, and then after that you remove glass, ceramics, or whatever left. And at the end of this material separation and material preparation, you end up with printed circuit boards, shredded printed circuit boards, which is the main value of e-waste. And that printed circuit boards contains copper, gold, silver, nickel, tin, palladium, and that's what we want to actually extract from these metals. So right now, status quo, there are two options. The green option, the good option, is it's going to smelters. So at least you know where it goes, what is the source, and you can trace it. The bad option, which is happening maybe with half of the e-waste in the world, is going actually to third world countries, and they burn it. They just burn it over there. They upgrade it by burning it just in an open circuit, and then they sending it to smelters in South Asia and smaller smelters. So that's the status quo. What we want to change is receiving those shredded PCBs and then grinding it to a powder form and start the leaching process. So it goes to our reactor, and we extract the base metals. We extract copper, tin, and nickel. And after extracting these base metals, whatever left, which contains all the precious metals, goes to the next reactor. And in the next reactor, we extract gold, platinum, palladium, and any other precious metals in there. And after that, we extract the silver.
So, Mohammed, if I may, Mohammed, again, so what's interesting to me is you're using electrochemical processes again here as well, right? In that second reactor, right?
Correct. So in all of our processes, the same thing, combining organic and electrochemistry together. And the reason that we are using electrochemistry is we minimize our chemical consumables. We actually, our main consumable is electricity. So electricity is actually what is oxidizing our solvents and organic bonds and oxidizing the metal and dissolving it into the solution. And the same, because of that, the electricity can be regenerated again and again. That's why we can reuse our chemistry over and over and over.
Got it. And as you described, yours 20% of the boards are copper, 4% are tin. Then you get the parts per million, 5 parts per million palladium, 10 of platinum. It's interesting you say 200 on PCBs. I've got a slide coming up on printed circuit boards. As you know, there's high-grade printed circuit boards that can well exceed 300 parts per million. So there's potentially some higher-grade gold streams in selective printed circuit boards if you know how to segregate. Silver's a problem for a lot of e-waste folks, right? We know the silver's there, but this becomes an economics game for, I think, a lot of conventional e-waste people. It's not always worth the extraction, right? It costs you more to extract than what you get out. So silver's always kind of been the dicey end of the spectrum, if you will. And again, you described a fairly closed loop system here where all these chemistries are used over and over again. I think that's just fascinating. Is there anything else you want to add there to this particular slide?
No, just to top it up, just to wrap it up, it's that we can extract the copper at the end of the process as a pure copper, so coming out as a copper cathode at the end of the process. It's the same with tin, and then at the end we have a concentration of PGM and gold and silver that goes to final refining to our refining partners.
Revival Gold, ticker RVG on the TSXV and RVLGF on the OTCQX market, is one of the largest pure gold mine developers in the United States. The company is advancing engineering and economic studies on the Merkur Gold Project in Utah and mine permitting preparations and ongoing exploration at the Bear Track Arnett Gold Project located in Idaho. The company is financed and currently focused on the completion of a preliminary economic study on heap leach gold resources at Merkur and continued exploration along 5 kilometers of underexplored structure at the company's multi-million-ounce orogenic gold system at Bear Track Arnett. For more information, please visit www.revival-gold.com.
People have this view of what, the e-waste is, and there's millions of metric tons of e-waste that's generated that gets put into the funnel, if you will, and, it's broken down and separated. But at the end of the day, we're ending up with only about 1,400 metric tons of precious metals, gold, silver, platinum, and palladium in particular. This excludes the copper value, and there's a great deal of value in the copper. There are separate streams that break off for some of these plastics and thermoplastics. But really, the whole purpose of e-waste, whether people like to hear it or not, most of it is a hunt for the printed circuit cards. That's where the valuable content resides. And people have this vision that we're just recapturing and reusing everything. No, actually, it's a pretty targeted and very specific process. And I know with most conventional e-waste guys that there's grading that you could do if you know how to separate these things. A low grade, typically, 70, 75 parts per million or lower, a medium grade, which could be, 150 to that 70. And then a high grade, typically over 300 parts per million is what's treated as a high grade. And this is the really valuable stuff. And there are a number of e-waste smelters that only want to deal with the high grade, right? That's where the economics are the best for them as recyclers. But I think what you're describing opens up the door more to some of these medium and low grade streams that others don't always want to contend with. Is that a fair assessment?
Yeah, it is actually. And the reason is that we can extract copper out of these materials with a very low energy and low cost process. And that is why I believe, and don't underestimate copper value in printed circuit boards. 20% of PCBs are copper, and we have almost the same value of gold and copper in printed circuit. So the value is pretty high on the copper side. And if you can extract the copper in an economical way, then that's the key. And that's why I believe our process will be attractive to recyclers and OEMs.
Okay. And then the last of the four buckets that you deal with, you mentioned hydrogen, and presumably here you're talking about PEM fuel cell stacks, for example, used in transportation that have platinum, a little bit of iridium, and potentially some ruthenium in the mix, or electrolyzers, which are very much iridium dependent with a little bit of platinum and ruthenium again. So three very specific PGMs. Is that the streams that you're talking about as feedstock from the hydrogen economy?
Yeah, we have actually two impacts in hydrogen economy. Number one is, as exactly you mentioned, we can extract these metals from end-of-life stacks, from end-of-life membranes, electrodes. Then we can extract platinum, iridium, ruthenium, and having it back into the circular economy. And the other one is actually we produce hydrogen because we are using electrochemistry, and our electrochemical reactions are through an electrolyzer that has been developed in-house. And we produce hydrogen that can be captured. For our PGM process, the hydrogen is not significant because our electrolyzers are small, and the hydrogen amount is not significant to capture it and use it in a meaningful way. However, for our mining operation and for copper mining, the hydrogen is pretty significant. So as I mentioned, we produce about 40 kilo of pure hydrogen per ton of the copper that we extract. And that hydrogen can be captured, can be compressed, can be used on site. So we actually eliminate hydrogen transportation, which is one of the major barriers in hydrogen development. So we can produce hydrogen on site, on a mining site, that can be used over there. You don't need to move it anywhere. That can be used just right there. You can have whatever you have inside that can be fed by hydrogen can be powered by the hydrogen produced on site, and we eliminate the transportation. And I believe we help the hydrogen transition on mining operations by implementing our electrolyzers and our process on sites.
Okay, got it. So let me try to wrap up this conversation. Really, the key question I have for you is the economics of this process. In the end, it always comes down to the economics. I know you're doing trials. You and I are both members of the International Precious Metals Institute. I know you've got sampling coming from all the major processors involved, looking at your process and benchmarking versus their own. Copper, you described, you're setting up this capability. You're getting close, but you're not quite there yet. E-waste, I don't know if you're able to sample those streams, but on lead demonstrations, are you able to effectively benchmark your cost versus the benchmark processes? And how's that stand? How does it stack up?
Yes, so I believe exactly. It's just whatever environmentally friendly you are, if you are more expensive, it doesn't matter. So the economy and cost is the key, and that's the key for developing a new technology. And for our PGM process, we are actually very confident that our cost is way lower than other existing methodologies.
I think so too. I think so too. The G2 I get from talking to all these people, our common friends in this industry, is you're looking pretty attractive in the PGM space for sure.
It's very low cost, very low energy, not really energy intensive, high yields, high recoveries, and we've got a lot of, I believe we processed more than 60, 70 tons of the material so far. And from next month, actually, our capacity is going to be about 150 to 100 tons per month of the materials that we're going to process through the demonstration plant that we built in Metro Vancouver. And I welcome you just anytime if you can have a trip to Vancouver. It's good to see our processing plant and our facility. It's a decent size. It's about 5 tons per day operation for spent catalyst, and it's up and running right now. So it's actually from last week we started operating this line. The unit economy is really good, really attractive, a very low cost.
If I may, Mohammed, one thing I didn't really emphasize in the slide deck, but on auto catalysts, there's really two populations. One is a gasoline, mostly light duty based population, which is palladium centric with a little bit of platinum and rhodium. And then on the heavy duty side, it's more of a platinum centric population. Unfortunately, in the heavy duty, there's a lot of confounding silica carbide and ti aluminum oxides substrates that are also in the mix that really confound, I think, most of the conventional smelting processes. That it mucks up the process, the sludge. It just creates operational downtimes and problems with smelters. And I got to believe your process is going to work well on those more complex heavy duty applications than a conventional smelting process. Is that right?
Exactly, absolutely right. And we have processed different type of heavy-duty materials and high platinum, high carbon content, zirconia, titanium. No problem. We can extract those materials without any challenges. It's actually very easy for us, platinum and palladium, because rhodium has another step to get to the yield that we need. So it's way easier for us to process those materials. Way lower cost, and there is no challenges processing of those high platinum heavy duty vehicles catalysts.
But I think there's an economic value proposition, if you will, for PH7 in that bucket in particular. As you know, the scrappers, the collectors, they literally are given about half the value for those heavy duty populations with the more complex, substrate materials that are in the mix. If you're able to successfully extract and process those, I mean, there potentially is a value proposition for the entire industry, right? It could be a win-win for everybody, right?
Exactly. That's absolutely right. And that's our goal, just to enable recyclers, suppliers to recycle more, collect more, and they can contact us and send us those materials that we can process it for them and give them the real value of those metals.
Great. Wow. So that was a pretty wide-ranging. Any closing thoughts you want to share, Mohammad, with our listeners?
No, thank you so much. That was amazing. Thanks so much for having me. It was fun. I had really fun time talking to you, as you know, as always. And just want to mention that we are open to business. If anyone wants to send us any materials for testing, for either in mining, for copper mining, or in PGM and recycling, please contact us. And we are here for business. And it's a new technology, but it's working.
Well, again, Mohammad, thank you so much for your time. Next week, we're going to have a conversation with a mining group, Platinum Group Metals Limited, who are the key stakeholders in a South African project called the Waterberg Project on the Northern Limb. So join us there next week. Again, this is Matt Watson with Green Rush, Mining the Energy Revolution. Join us next week. Like and subscribe. Thanks, everybody. Until next time.
Green Rush, Mining the Energy Revolution with Matt Watson.